Since there are no questions on factoring, let's go to page 468. We'll start section 10. It says compare your choices from number 3 of getting ready for the lesson with those of your group members. We actually did that yesterday. And it says then use this graphic to answer the questions that follow. So bottom of the page, number 2. According to the graphic, how many daily Facebook users are there?
I mean, there's 63.46%.
Well, that's a percent. That doesn't tell us how many.
Shoot.
There's actually 3 graphs within that graph.
Okay, there's one, right?
Mm-hmm. There's a bar graph, a line graph, and a circle graph.
640 million, would it be? Up at the right, like right here.
And that's total registered users, and that doesn't
Oh.
tell us how many daily Facebook users there are.
Jeez. Okay. Okay, so it'd be 310, right? Because
What's
this
the
is
M
daily.
mean? It says 310M.
Is it million?
It is million, yes. So 310 million people. Do you think this statistic represents the United States or the world?
The United States.
You think it's the United States? So everybody in the United States uses Facebook?
Oh wait, no, the world. Sorry, I was thinking, no, everyone has Facebook, it seems.
Yeah, so that number, the 310 million, is slightly less than the U.S. population. And since not everyone in the U.S. is on Facebook, it must be the world. Or the statistic must be for the world.
I think everyone has Facebook. There's even Facebook animals that have Facebook.
Okay, next page, number 3. Compare the evolution graphs, which shows millions of users for Facebook, Twitter, and MySpace. Interpret the graphs. Where's the evolution graph? What do they mean by that?
The years?
Okay, there you are, down at the bottom with the line graph. So interpret that graph. What's it telling you?
That there are more Facebook users, and then there's like less people on MySpace.
More Facebook users. Fewer people on MySpace. Anything else?
Twitter has gone up since 2008.
Okay. In fact, it's gone up pretty quickly since 2008. Anything else?
I don't think so. I don't think so.
Well, not only is there more Facebook users, but that went up pretty quickly too.
That up in 2008.
Well, even before that, it was going up quickly. Maybe all the way back to 2006, it started taking off.
Yeah.
Okay, part B. What type of graph is the bar graph on the side that shows the daily unique visitors to each site? That bar graph has a special name.
I don't know.
Starts with a P.
A P? Perpendicular.
No, not perpendicular.
I really have no idea.
Pareto.
Oh, yeah, see, that's not that.
Number 4. Which company's growth took off earlier, Facebook's or Twitter's? And which took off faster? Explain how you know.
Facebook for both.
Facebook for both? Yep.
Yeah.
And how do you know that?
Because you can see on the graph. Because, like, Facebook's, like, started at 2006 and Twitter started going off at 2008.
So 2006 versus 2008. Now how do you know it grew faster?
Because it went up all the way to 600 million and Twitter is 200 million.
Okay. 640 million versus 200 million. So you could also say, looking at the graph, that the one for Facebook is steeper.
Steeper? Oh, yeah.
So it grew faster. Number 5, Facebook's growth is impressive. Do you think it can continue to grow at this rate forever?
No, because there will probably be, honestly, a new website that people can go on.
Okay.
In my opinion. I mean, like, because
Could
MySpace
be
used to be
some
popular.
new website. But what if there wasn't a different website?
Then yes.
It could continue to go like that forever?
Probably. A lot of people, like, are just getting Facebook, like, all the time. Like, always on there.
That's true. They're getting it quickly. But if it keeps
But maybe
growing,
not forever.
probably not
everyone's gonna
forever.
have it.
we're going to run out of people. If
True.
it keeps growing that fast, we'll run out of people. So we can say there's a natural limit based on the world population. As we have seen, social networking sites are popular with many people. These sites are also popular with businesses and advertisers because of the possible marketing opportunities. A website, story, or link can go viral and reach millions of people in a very short period of time. We explored the idea of viral marketing in the first cycle. Let's revisit this type of explosive growth and apply the knowledge we have gained since lesson 1.17. Number 6. Suppose a company has 100 customers, each of whom receives a link to a website. Each customer shares the link with 2 friends on their Facebook walls. Assume it will take 1 day to share the link. Let's explore this numerically and then use a formula to generalize the number of people who will receive the link.
We did, like, something like this before.
We did, yes. Section 1.17.
Dang.
Okay, so we're going to complete this table. So day 0, there's 100 recipients. The calculation is 100. Calculation with exponent still 100. So how many recipients will there be on the second day? Those 100 people are going to send the link to how many people?
2, right?
2. So how many recipients would there be the second day?
Wouldn't it end up being, would it be 200?
It would be 200, yes. 2 for every 100. So our calculation then, over here in the middle, we would be taking our original 100 and multiplying by
2.
2. And with exponents, we really don't need exponents at this point yet. It's still 100 times 2. So now we have 200 recipients. How many recipients will there be the next day?
200 times 2. So it would be 400.
Okay, yep. Whoops, that's an ugly. Okay, so we had what we had before, the 100 times 2, and then we took that times 2. Now we can use exponents. We have the 100 times 2 to the second power. So far, so good?
Mhm.
Okay, what do you think's on the next row?
It would be 600.
Not 600.
No, wait, 800.
800, because you have to double it. What about in the middle?
It would be 100 times. Is there a way to shorten it so you're not like 100 times 2 times 2 times 2?
Well, we're not going
No.
to shorten it here, but the way to shorten it is using exponents in the last column. So how would you write it with exponents?
Wouldn't it be 2 to the third power?
And don't forget the 100
Or, well, yeah, 100 times 2 to the
times
third
2 to the third power. What about the next row?
It would be 1,600.
1,600. In the middle?
100 times 2 times 2 times 2 times 2.
The 100 times 2 times 2 times 2 and times another 2. Last column?
100 times 2 to the fourth power.
100 times 2 to the fourth. Next row.
3,200.
3,200. In the middle?
100 times 2 times 2 times 2 times 2 times 2.
100, and then we're going to have 5 2s. Last column?
100 times 2 to the fifth power.
Okay. Well, we have one more row and we only have to do the last column. So if our day is n, we need to have a calculation over there with exponents. What do you think?
Like we add all these?
No, we're not going to be adding
Or
all of those.
Would it be 3,200 times 2?
No, because that would mean that n is 6 and we don't know that. We want a general formula. Let's go back up. We're looking at the first column and the last column. We need a formula over there in the last column, right?
Yeah.
Okay. So let's look at how the days are related to that last column. For day 0, we just had 100. For day 1, it was 100 times 2. And there's really an exponent of 1 on that 2, even though you don't see it there. Okay. The next day, day 2, it's 100 times 2 squared. And then the third day, you have 100 times 2 cubed. What do you notice about the day and then that calculation over there?
The exponents are just going up one more.
It's actually the number of days, right?
Mm-hmm.
Okay. So now if we want a general formula for n, what do you think it would be?
I think this would be 100 times 2 to the sixth power.
Not sixth power.
Oh, jeez.
What is our day?
N.
There you go, to the n power. Whatever day we're on, we can put the number in there. Like if maybe we want to skip up to the 10th day. We could put the 10 in for the exponent and figure it out. We wouldn't have to find all the numbers in between. Okay, let's try B. Use your calculations to generalize the number of people who receive the link on the nth day. We actually already did that. The only thing is they wrote it a little bit differently in this answer than they did in the table. What they did was they said 100, and then they have 2 to the nth power in parentheses. But it's really the same thing that we had in the table. Part C. There are 2 key numbers in the formula, 100 and 2. What does each represent?
Well, 100 represents the people, and then the 2 is like their friends.
Okay. So 100 is the starting number of people. And the 2 We can call that the growth rate, or it's a 2 because we're doubling. Questions on C?
Nope.
Okay, letter D. Use guess and check to find when the number of people who receive the link reaches 1 million. So take some time and see if you can plug in some numbers and find out how long it would take to reach 1 million people. Our biggest number in the table was 3,200, so you have a ways to go. Okay, so guessing and checking, you should find that it takes the 14th day to go over 1 million. Letter E. Rewrite the original formula, assuming there are 500 customers to start. So our original formula, the number of people is equal to 100 times 2 to the nth. But what if we change the number of original people to 500? How does it change?
Just put the 500 in for where the 100 is.
Yeah, put the 500 in for the 100. And letter F, rewrite the original formula, assuming each customer will post to 4 friends' Facebook walls.
So, I mean, I don't know if, are we still doing the 500 or the 100?
We're going back to the original formula.
So it would be equal 100 and then 4 to the n power.
There you go, times 4 to the nth power. Letter G. Combine parts E and F to create a formula with the assumption of 500 customers initially who will each post to 4 friends' Facebook walls. So what would that formula be?
Maybe 500 times 4. Wait. Yeah, it'd be 500 times 4 to the n power.
That is correct. Yep. Letter H. Use guess and check to find when the number of people who receive the link will reach 1 million using this formula.
I'll start with a 4.
Okay, so using guess and check, you should find that it will take 6 days to reach 1 million. So letter I, what lessons can we take from this that marketers could use?
They can do math. They can do this.
So what should marketers do?
Well, I guess they could find out, like, how many, I don't know, how many things people are posting on Facebook.
Well, what happened when we changed the number of beginning customers and the number of people that they each reach? We got to 1 million a lot quicker, didn't we? It was 14 days versus 6 days.
Yeah.
So the more people you begin with, and the greater the growth rate, the more quickly the information can spread. So they'll want to get it out to a lot of people right away and hope they pass on the information. In the box, exponential function. An exponential function is an equation with the following form where the variable is in the exponent. So we have y equals a times b to the x power, where a is the starting value and b is the growth rate. The value of a is a non-zero real number. The value of b is a positive number that is not 1. If b is greater than 1, the graph will be increasing. If b is between 0 and 1, the graph will be decreasing. X is any real number. So for example, y equals 5 times 1.03 to the x power is an exponential function with an initial value of 5 and a growth rate of 1.03 that reflects an increase of 3%. Remember that from early in the semester when we were finding a 3% increase, we would multiply the number by 1.03? Pardon me? Remember that? Okay. Also, y equals 10 times 0.80 to the x power is an exponential function with an initial value of 10 and a growth rate of 0.80. This reflects a decrease of 20% and is described as exponential decay. So we did some earlier where if we wanted to find a percent of decrease, we would take 100% and subtract whatever our decrease was. In this case, you would subtract 20%. That would leave you with 80%. That's where they're getting the 0.80. Questions? No. Okay, let's try number 7, part A. Suppose y is an exponential function with an initial value of 7 and a 10% growth rate. Find an equation for y. So we'll have y equals to something. What do you think? That is correct. 1.10, or you could just say 1.1. You don't necessarily have to have the 0 on the end.
To an x power?
And we need the x power. So you can have the x inside the parentheses. That's what we did before. Or you could actually have the x on the outside of the parentheses. It doesn't really matter. Letter B. Suppose y is an exponential function with x, or of x, with an initial value of 7 and a 10% decay rate. Write an equation for y. So y equals...
Should we like flip it?
No, we're not going to flip it. What's our initial value?
Like 7.
7, so that part is the same. Now when we had a 10% growth rate, we added that percent on to 100%. That's how we got the 1.1. So what if there's a decay? Instead of adding, what are we going to do? Subtract. So what's 100 minus 10?
9.
And how do you write that as a decimal?
0.9.
So 0.90, or you could just say 0.9. I'm going to put the x on the outside this time. It really doesn't matter, like I said on part A, whether the x is inside the parenthesis or outside. It's really the same. Questions on A or B?
No.
Okay, number 8. One of the most popular paid apps is Doodle Jump, which has been downloaded at least 10 million times in its first 2 years. Have you ever heard of Doodle Jump?
We actually had it, but I got it for free.
Oh, really?
Yeah.
Well, look at the source. Most people have never heard of Doodle Jump, but look at the source. Angry Birds. Okay, 8A. If the app cost 99 cents per download, how much money was made in the first 2 years from Doodle Jump?
Wouldn't it be 10 million times, or, yeah, 0.99?
Very good. There's 10 million downloads. Times the 99 cents. So 10 million would have 6 zeros after the 10. Multiply by 0.99. Or actually, you could just leave it as 10. 10 times 0.99 gives you...
There's 10 zeros or 6 zeros?
Don't put the zeros in. Just take the 10 times 0.99. What do you get?
9.9.
So it's really just a matter of moving the decimal over 1. So it's 9.9, but then don't forget to put the million on there. And the dollar sign. $9.9 million. A lot of money for Angry Birds. D. It has been reported that the team behind the app has made approximately $7 million after paying Apple and Google. What percent cut of the revenue did Apple and Google receive?
I wish there was another number in there because I don't really know how to.
Well, there's more than one way that you could work this out. Any ideas at all on how to start?
Could it be
They brought in $9.9 million, and then it says that the team behind the app made approximately $7 million after paying Apple and Google.
Would it be 9.9 million divided by 7 million?
Ooh, close. Flip those. If you flip them and take the 7 million and divide by the 9.9 million, you'll find the percent that the team received. So take the 7 and divide by 9.9. And I believe you'll get a long decimal number.
0.70? Why?
0.70 repeating.
Yeah.
So 0.70 repeating. What percent would that be? If you rounded to the nearest whole percent?
70?
Not 70, because if we continued out that long decimal, the next digit after that 0 would be a 7. So that's going to make it go up to,
So this would be 80?
not 80, but it's not 70 either. It would be,
75?
no. You have the two decimal places. You need to look at the next decimal place, that's 7, to determine whether that 0 stays a 7 or whether it goes up to a 1.
It would be 71 then.
There you go. 71%. And again, that's what the app, or the team behind the app, what their percentage was. How do we figure out then the percentage that Apple and Google received?
I don't know how much they I guess would it be like 100 minus 71?
Exactly. 100% minus 71% would be
29%.
29%. Next page, part C. If the app has been downloaded 10 million times already and is currently being downloaded approximately 500,000 times per month, create a table of values to assist you with writing a linear model to represent the number of downloads in millions. Okay, so at month 0, that's our starting place. That would be now. The D is the number of downloads, and we've had 10 million so far. Okay, so at the end of the first month, how many downloads would we have? And remember, we want linear growth. So what's going to happen in that second column?
It's going to go up.
It's going to go up, and from one to the next, it should go up by the same amount. Okay? So how many will we have at the end of that first month?
Well, there's 500,000.
500,000 per month. What is that in terms of a million?
I like divide it by a million. I'm so lost.
What part of a million is 500,000?
Wouldn't that be the half part?
It would be half of it. So if we had 10 million before and we add half a million, now we would have 10.5 million. Does that make sense? 500,000 is really half a million. So month 2
would be 11.
we would have 11 million.
And 3 would be 11.5.
And 3 would be 11.5.
4 it's 12.
4 would be 12.
And then 12.5 is 5.
5 we would have 12.5. Okay, so now we actually have to come up with the linear model or the equation. So D is really our y. Remember our general form is y equals mx plus b. So in this particular case, x would be, it's going to get really confusing.
Wouldn't x be the m?
Yes, the number of months. And I'm going to write months instead of just the m. And the y would be
The downloads.
the number of downloads, the D. Okay, so our equation, we will have D is equal to, do we know the y-intercept from the table?
No.
Yes, we do.
We do.
One of those points is the y-intercept. Which one is it?
Well, wouldn't it? Wouldn't it be in the middle?
Not in the middle.
So it'd be the 0 and the 10.
There you go. There's our y-intercept. So that actually tells us what b is. We can also find the slope from the table. Instead of writing our usual m for slope, I'm going to write slope. Otherwise it's going to get really confusing with all the m's in there. So slope is what?
Would it be like 5 and 12.5?
No, we're not really looking at specific points this time.
Oh.
The slope is the change in the y's over the change in x's. So if you're looking at the y's, which in this case is the d's, they're increasing as we go from one to the
every
next.
5.
0.5, okay? It keeps increasing 0.5. And what's happening in the m column then?
1 by 1.
They're increasing by 1. So our slope is actually 0.5. So if we continue with our formula over there, we put d in for the y. We now know that the slope is 0.5. And now we'll use m for the months. Plus our y-intercept, the b value is 10. Phew. Questions?
No.
Okay, let's try letter D. Letter D. According to the linear model, how many months will it take to reach 100 million downloads? So we can use the linear model, that equation that we came up with. D is equal to, whoops, that's 0.5 plus 10. How many months will it take to reach 100 million downloads? What do we do?
Would it be like 0.5 times 100 plus 10?
So 100 is the number of months?
Wait. No, it's a download.
It's the download, so we need to put the 100 in for
The D.
D. So 100 is equal to 0.5 m plus 10. How do we solve this equation?
Wouldn't you like do these two and then divide it?
We can't do anything with 0.5 m plus 10. They're not like terms. One has an m and one does not.
So you would just do 10 and 100?
Well, we have to do something with 10 and 100. What do we do?
Subtract them.
Subtract what?
The 10 from 100.
Okay, we're going to subtract 10 on both sides. So now we have 90 is equal to 0.5 m. Next step.
Now would you divide 90 by 5.5?
Yes, now we divide both sides by 0.5.
180.
So that will be 180 months. So that answers the first question. And now they want to know how many years that will be. What's that?
It's like never ending.
Never ending. Okay, so we have 180 months
Can you do
over
100
1.
divided by 12?
Yes, we need to divide by 12. There's 12 months in 1 year.
15 years.
15 years. Okay, letter E. If the app has been downloaded 10 million times already and the number of users is growing 5% each month, create a table of values to assist you with writing an exponential model to represent the number of downloads in millions. So our table is going to start out the same way. At month 0, we have 10 million downloads. So last time in part C, we had a linear relationship. So for the second column, we kept adding something in the second column. This time we have exponential, so instead of adding, we're going to be doing something different in the second column. What are we going to do?
Multiply.
Multiply, yes. Okay, so month 1. So we're going to have to take 10, and what are we going to multiply by?
0.5 or 0.05.
Very close. 0.05 would actually tell us our increase. So if we multiply by 1.05, that will tell you you'd have the 10 plus the increase in there. And what do you have?
10.5.
10.5. So far the tables are identical.
Well, it's going to go up by 5s again.
Okay, so for month 2, now instead of starting all over, just take what you have in your display and take it times 1.05. Because what you have is going to increase by 5%, correct?
Mm-hmm.
Okay.
$11.025.
Okay, 11.025. Now don't put that in your table just yet. I'll explain why. What they did was they took that number and they rounded to 2 decimal places. So what would you put in the table if you rounded to 2 decimal places?
Wouldn't it just be 11? Because
Well, that's rounding to a whole number. What if you want to round to 2 decimal places?
11.02 or
Well,
11. Wait. What am I?
does the 5 make the 2 go up, or does it stay a 2?
So it would be it would go up
It would.
to a 3.
Yes, there you go, 11.03. Now, month 3, keep that number in your display that you had, the 11.025, and multiply that by 1.05. And I think you're going to get an even longer decimal,
Wait, did you say 0.05?
1.05.
Oh, shoot.
Okay, so you had 11.025, and multiplied by 1.05.
11.57625.
There you go. 11.57625. But round that to 2 decimal places, and what would you have?
11.58.
There you go, 11.58. Month 4. Take that long decimal that you have in there and multiply by 1.05 again.
12.1550625.
Long decimal. Round it to 2 decimal places.
12.16.
There you go, 12.16. Month 5.
12.76281563.
And if you round that to 2 decimal places, what would you have?
12.76.
12.76. Okay, our exponential model. So our number of downloads is equal to, what was our initial value?
Would it be the 5%?
Not 5%.
Okay, 10 million downloads.
10 million downloads was our initial value. And we had 5% growth, right?
Mm,
So what did we multiply by every time?
1.05.
That's what goes in here. And then we have that to the nth power, number of months. So we worked them out a little bit differently in the table because we just took the number that we had in our display and we multiplied by 1.05. But if we were to use the formula, for example, for the 2, we would have had 10 times 1.05 to the 2nd power. And that would give us the 11.025. For the 3rd month, if we had taken 10 times 1.05 to the 3rd power, that would have given us our answer as well. It's really a matter of multiplying one more time by the 1.05. Okay, letter F. According to the exponential model, how many months will it take to reach 100 million downloads? How many years is that? You cannot solve this exactly with the algebraic methods learned so far, but you can estimate an answer. Okay, so our model was downloads is equal to 10 times 1.05 to the nth power. How many months will it take to reach 100 million downloads? What do we do? 100 million equals 10 times 1.05 to the nth power. Well, there is a little bit we can do with that. What can we do?
What do you mean, like, do like 10 times 1.05?
Can't do that because of the exponent. We would have to know the number of months and take care of the exponent before we could multiply. There is something we could do to make it a little bit easier.
I don't know. Would you like subtract 10 from 100?
Not subtract,
Add?
not add.
Divide?
Yes, you would divide. See how it's 10 times the 1.05 to the nth power? So the opposite of multiplying is dividing. So we're going to divide by 10. A 100 divided by 10 is 10. So at this point, we don't have a method to solve that when our variable is in the exponent like that. But you could use guess and check. So you can put a number in for M and see if you get 10.
What do you mean get 10 from the...
Because 1.05 to some power has to equal 10. What are you substituting in?
I'm going to do a 5.
Even though 47 is closer to 10 than when you use the 48, the book used 48 just because they were estimating, and it actually works out much nicer for months, or when you convert to years. So we're going to say the number of months is approximately 48 months. And now when we convert to years, 12 months in a year, how many years would that be?
4.
4 years. Okay, well, C through F, you will definitely see again. It's definitely on the test, and I'm guessing you'll probably see it either in a problem of the day or a quiz before we get to the test. Okay, we will stop there for today so that you have time for the problem of the day. So we'll continue with section 10 tomorrow and also start working on logarithms. Now, on this problem here that we just... Logarithms are not in the book, so you'll have some more handouts. Like this problem here, we said we didn't have methods to solve it because our m was in the exponent. Logarithms gives us a way to solve a problem like that.
Of course does.
Okay, so something to look forward to tomorrow.